All right, in this video, I'm going to continue with section 6.3, but I'm going to be focusing on the power reducing ones at the start, and then we'll do a few half-angle problems as well. All right, so one of the questions you might be asked to do is to rewrite an expression like sine x raised to the fourth power, sine to the fourth power x. Rewrite that so you don't have any powers of trig functions bigger than 1. So you reduce the power to where you only have like sine to the first power or cosine to the first power in there. So we're going to be using the power reducing formulas. And to start with, I'm going to be using this one because I'm going to rewrite or think about sine to the fourth x as sine squared x times another sine squared x. And remember, these are just function notation. So if it helps, go ahead and put the argument in parentheses. Okay. All right. So if I do that, then I can use the power reducing formula that says that that's going to be equal to 1 minus cosine 2, and I should have used x on that since they started with x's, not thetas. 1 minus cosine 2x, that's not squared x, that's 2x over 2, and another 1 minus cosine, and again, be careful, 2x over 2. Don't get sloppy or you'll misunderstand, not be thinking correctly about what you have. So we're multiplying fractions. So remember, you multiply straight across. So that's going to be a 4 in the denominator. So this is going to be 1 minus cosine 2x minus another cosine 2x, and then plus cosine squared 2x. Okay. So let me put my like terms together there in the middle. I have 2 cosine 2x's. So 1 minus 2 cosine 2x plus cosine squared 2x. And these are just the arguments now. So let me put those in parentheses. So you see that, and all of that's still divided by 4. All right, so I still have a power other than 1 right here, so I need to rewrite that one. So now I'm going to move to this formula. Now be careful, okay, be careful, all right? So cosine squared, whatever your angle is, equals 1 plus cosine 2 times that angle. But see how our angle here, let me put it in red. This is the tricky part. The angle is that. So this is really 2x. So this is going to be a 2x where the theta is. So you have to be careful when you use that, okay? So that part right there is where the mistakes are typically made. So this is 1 minus 2 cosine 2x. That's what we already had. But then that formula said you would do 1 plus cosine 2 times your angle, but your angle now is 2x. So your angle is 2x. So make sure you have that 2x on that. So it's 1 plus cosine 2 times your angle, all divided by 2. And then all of that is divided by 4. Okay. All right, so what we have is a couple things we got to do. One of them is I have a complex fraction, so I might want to get rid of that. Okay, so what I can do is multiply by 2 on top, as long as I multiply by 2 on the bottom. And then this isn't a squared right here. Let me write that even better. That's not a squared, right? That was the 2 times your angle you're supposed to do. The formula said to do 2 times your angle. It's just your angle itself was 2x. So this will become 4x when I rewrite it. All right, so here we have a 2. When that gets distributed to the second term, I have minus 4 cosine 2x. Distributed to the third term, here we did it so it would knock out the denominator. So I have just plus 1 plus cosine, and then I'm not distributing anything. I'm just working out 2 times 2x, which is 4x. And then all of this is now over 8. Okay. All right, so let's see now. So that's a 2 and a 1, which is going to be a 3 minus 4 cosine 2x plus cosine of 4x. And all of that's over 8. So let me go ahead and divide that 8 into each little piece. Okay, and then I'm noticing right here that I could simplify that one. That would be a 1/2 right there. And so my final answer, let me do it in red, would be 3/8 minus 1/2 cosine of 2x plus 1/8 cosine of 4x. Okay. Right, so that's one thing you could do with the power reducing formulas. We don't use those a whole lot, so I just want to do one example. Okay. All right, so let me see if I can get it to let me move down. Yeah, good. All right, now let's go ahead and do a couple half-angle ones on the same page. The kind of problems they might ask you to do related to half angles. All right. All right, so for the half-angle formulas, half-angle examples, what will happen is you might be asked to do something like the cosine. Cosine is more interesting, so that's why we're doing cosine. Maybe the cosine of 112.5 degrees, or maybe the cosine of 105 degrees. And one thing you could do is try to split those up. You know, like earlier, we could do something like the cosine of 105 by trying to split it up into angles that we could find on our unit circle. And they'd be wanting us to find the exact value, so that means no calculator. And so you could use a unit circle, or you could use special right triangles. And so we've done one like this type of thing before, and we could think about 105 being 60 and 45. And so we could use cosine of 60 plus 45 and use that formula. But we're being asked to try to think about it in terms of a half angle formula. So we're going to look at what we can do there. All right, so let me go grab the half angle formula for the cosine. So let me get you to look at that. I'll just write it again right here instead of scrolling back. So the cosine of, where can I write it? Let me see if I can squeeze it in right over here. No, I'll just do it big. So the cosine of alpha over 2 equals plus or minus. It's not both. It's that you have to decide which one it is. It's not both. It's one or the other, but you have to determine that based on the quadrant you wind up being in. So you have to be careful there. Okay. So the cosine of alpha over 2 equals plus or minus the square root of 1 plus the cosine of alpha, all divided by 2. Okay. And then you've got to decide which one of those it should be. All right, so if we're trying to do the cosine of 112.5 degrees, I can't really split that into special angles. And then I know, since I'm in the half angle formula, that maybe what I could do is this. Maybe what I could do is think about twice that angle for a second. So do you see how the 112, if I doubled that, how that would be 225 degrees? So 112.5 degrees is the same as 225 degrees divided by 2. By thinking of it like that, I now have it where it looks like I can use this half angle formula with theta, and this is important, with theta being alpha being 225 degrees. Okay. So you got to think about that and think about where 225 degrees is. That's 180. 225 would be right there. Okay. And that's at that 45 degrees past 180. 225 would be right here, 45 degrees past 180. So the reference triangle for that is 45 degrees. Okay. Here, let me make that bigger so I can get you to think about that carefully. All right, so 225 is here. This is 45 degrees, so it's the reference angle for that. And drop your perpendicular right there. And so I'll be able to figure out the exact value for the cosine of 112.5 by using this formula together with what I know about the cosine of 45 degrees. All right, so here's how we do it. So we're doing, I'll leave it red. We're doing the cosine of 225 over 2. Okay, so we're going to come in here and we're going to do 1 plus cosine. And this right here is really 225 all divided by 2. And outside here, whether you put the plus or the minus outside here depends on what this angle is. So the 112.5 degrees. Okay. So I really got to think about both of those things. I got to think about how the cosine of 112.5 degrees, that's in the second quadrant. So I know that 112.5 degree, the cosine of that should be negative. So I need to think that. So it's really tricky. You got to think about that. So that's going to be negative, I know. And it's not because of the 225, it's because cosine of 112.5 would be negative. All right, then I go in and I work on simplifying this. And when I do the cosine of 225, I basically think about it being square root of 2 over 2, right? But I'm in the third quadrant, and so I know my cosine is going to be negative. So right there, I'm going to have, and I might as well just change that to a minus. I know I'm going to have a negative square root of 2 over 2. So 1 minus square root of 2 over 2. There. Okay. All right, so now we've got to simplify this. It winds up being kind of interesting, like with a radical inside of a radical. So we have that complex fraction issue happening again. So how about we multiply the top by 2 and the bottom by 2? So that'll give us 2 minus square root of 2 all over 4. So I distributed the 2, and the 2, when it went to that second term, knocked out that denominator. And then at that point, I wind up with a negative 2 minus square root of 2. And then in the bottom part, when I do the square root of 4, that'll just be 2 outside of it. And so that would be the exact answer for the cosine of 112.5. Okay. All right, so let's try another one of those. So let's think about maybe the cosine of 105. So we're trying to do the cosine of 105 degrees. Well, if we were allowed to, we could use the formula for the cosine of the sum of two angles. We could use 60 and 40, but they wanted us to use a half-angle formula for that. So we're going to set it up the same way as the other one using the half-angle formula. And so we're going to wind up having the square root of, and we're going to put something inside here. Let me go down one more step before I do that. We're going to wind up using a half-angle formula. So let's first think about how 105 degrees is 210 divided by 2. Okay. All right, but think about the 105 for just a minute. That angle, again, is in the second quadrant. So you know this is going to be negative. So that determines that. Outside the square root symbol, you know it's negative. Okay. Then underneath there, I'm going to have 1 plus the cosine, and alpha in the formula is whatever was on top. So that's the 210 degrees. And that's going to all be divided by 2. Okay, so I got to think about 210 now. So 210 would be 180 and a little past that. That's 210. which means this would be 30 degrees past that. This is why I really was trying to get y'all to think about those reference angles back in the earlier chapter, because I use them a lot when I get here. All right, so that's really going to be related to a 30, 60, 90 triangle. So if that's 30, this is 60, it would be 1, 2, square root of 3. And then I like to think about the quadrant I'm in and go ahead and put the signs that I would have. So since this is to the left, it would be negative square root of 3. And since this is down, it would be negative on the 1. Okay. So let's see how that affects things. So this is going to be negative square root of 1. And then cosine of 210 would be the same as the same number part as the cosine of 30, and then I just have to adjust the sign. So really, if you put the signs on these values, you can get the cosine from that. So it would be negative square root of 3 over 2. So this is going to be minus the square root of 3 over 2, all over 2. Okay. All right, so you got the complex fraction idea going on. So go ahead and get rid of that little denominator. So that's going to give you a negative square root of 2 minus square root of 3 over 4, which would be negative square root of 2 minus the square root of 3 all over just 2, because the square root of 4 is a perfect square. Okay. All right, and then let's try one more thing. Let's verify. Let's do another identity. Okay. So the last example I want to do is look at verify that the tangent of theta equals sine of 2 theta over 1 plus, make sure I've written that right, cosine 2 theta. I got sloppy and I couldn't tell whether it was supposed to be squared or not. Okay. All right. So looking at that, I might want to start with the right-hand side because it's more complicated and show that it equals tangent theta when I'm finished. So let me do that. And so I'm going back to some formulas for sine of 2 theta, and it equals 2 sine theta cosine theta. All right. And then cosine 2 theta. There's a lot of options for what I do for that one. And so sometimes I'm not real sure which one I need. So I kind of look at what I'm trying to get is like tangent. And so I'm trying to get tangent to show up here. So I'm thinking if I could get a cosine in the bottom, so I'd have sine over cosine, that would be good. So I'm going to try replacing cosine 2 theta with cosine 2 theta with 2 cosine squared theta minus 1. Okay, so I replace this with that. Okay, now what made me think to do that is I needed tangent, and so I wanted sine over a cosine. That's why I thought that might work. So here I have 2 sine theta cosine theta over, and then the ones are going to cancel out, and I have 2 cosine squared theta. Okay. So now 2's can cancel out. And then don't forget what that denominator really is. It's really 2. The denominator is really, oops, the 2's were already out of there. The denominator is really cosine theta times cosine theta. That might allow you to see better that, I'm trying to get to a red pen, all right? So now the cosine can cancel, and then sine over cosine leaves me with tangent of theta. So actually, I should have put that one, back in, maybe back with the double angle formulas and not wait until now to do that. All right, why don't we try one more verifying? How about one like this? What if I wanted to verify that tangent of alpha over 2 equals, this is a verify, this looks pretty messy, equals secant alpha over secant alpha cosecant alpha plus cosecant alpha. Oops, cosecant. Starting to lag just a little bit. Plus cosecant alpha. Okay, so that's what I'm trying to verify. Well, I think what I would do is probably start with the right-hand side because it looks more complicated. And maybe get rid of the, oh man, I'm in trouble here. Hold on a second. Get rid of the secants and cosecants and write them in terms of sines and cosines. That might help. All right, so why don't I just do that? That's probably the most straightforward thing. So this would be 1 over cosine alpha. This would be 1 over cosine alpha. This would be 1 over sine alpha plus 1 over sine alpha. Okay. Then I've just made a complex fraction. So let's use that trick I showed you for simplifying complex fractions. I'm having trouble changing colors. What I wanted to do, let's see if I can just go there, is take and multiply. Look at these little denominators and multiply by those denominators. I probably should do one more step before I do that though, so you see why this will work. So see down here, this is 1 over cosine alpha sine alpha. When you multiply straight across. Okay, so now let me do it. So now let me look for a denominator that I could use, something I could use as a least common multiple of those that would knock them all out. And that would be the cosine alpha sine alpha. So I'm going to multiply here by cosine alpha sine alpha and here. And that cosine alpha gets distributed really. So let me show that step so you really see what cancels out. So we have it here. There's only the one term. But see, like here, that cosine alpha sine alpha gets distributed to it and to this one. And let me change that color on this guy. Why aren't you erasing? And this, put it in blue like I did the others. Okay, really helps to see that step anyway. So the cosines go there. Both the cosines and the sines go away there. And here, the sine cancels out. Okay, so I need to get some more paper. Let's see if it'll let me move down. Okay, so now we're just using a lot of little algebra skills to try to get this to turn into the tangent of alpha over 2. Okay. Be safe for a minute. I think I'm starting to. Uh-oh. I think I've overburdened it for a bit. Tell you what, I'm going to stop my video and I will finish that and post the finished work, but I just won't talk it all through here. You'll just look at it in the video, but I think it just got to where it was overburdened for a moment.